There is a rule in this universe that nothing is supposed to break. Nothing with mass, nothing carrying information, nothing that exists as we understand existence, is supposed to move faster than light. Albert Einstein wrote that rule into physics in 1905, and in more than a century of testing, poking and trying to break it, no one ever has. And yet, right now, somewhere above your head, something is moving faster than light. Not in a lab, not in theory, in observed, measured, photographed reality. Telescopes have recorded it, physicists have confirmed it. And the strange part is this: it doesn't break Einstein's law at all. It exposes something we misunderstood about the law itself. This is the case file on speed. Not the speed of light, the limits of it, the loopholes around it, and the very specific, very narrow definition of faster that most people never learn. Because when scientists say nothing can go faster than light, they don't mean what you think they mean. And once you understand what they actually mean, you start seeing things breaking the speed limit everywhere. Your shadow does it, the edge of the universe does it, beams of light inside prisms do it, even empty space itself does it. We are going to walk through each of these, one at a time, the way an investigator walks a crime scene, establishing what's true, testing what's not, and resolving every gap before we move to the next. Let's start with the law itself, because you cannot understand an exception until you understand the rule it's exempting. In 1905, Einstein published a paper called On the Electrodynamics of Moving Bodies. Buried inside it was a conclusion that would reshape physics for the next century. The speed of light in a vacuum, roughly 299,792 kilometers per second, is not just fast, it's a structural constant of the universe itself. Not a speed limit imposed by engineering or friction or the limits of our instruments, but a hard ceiling built into the geometry of space and time. Hermann Minkowski, one of Einstein's own former professors, took this idea further in 1908, showing that space and time aren't separate stages for physics to play out on. They're fused into a single four-dimensional fabric, now called space-time. And light speed isn't just fast within that fabric, it's the conversion rate between space and time themselves. Here's why that matters. If you could accelerate an object with mass, you, a spaceship, a single electron, up to the speed of light, the energy required wouldn't just be large, it would become infinite. Not extremely difficult, infinite. That's not a limitation of our rockets or reactors. It's baked into the mathematics of relativity, confirmed again and again in particle accelerators like CERN's Large Hadron Collider, where physicists have pushed protons to 99.9999991% of light speed, and never, not once, crossed the line. So the rule holds for anything made of matter. Nothing physical, nothing with rest mass, gets to the finish line, let alone past it. But here's the case file twist. Einstein's law was never actually nothing can move faster than light. That's the popular version, the one that got simplified for textbooks and repeated so often it became gospel. The precise version, the one written into the actual physics, is this. No signal, no information, no cause and effect influence can travel faster than light. That's a much narrower rule than nothing can move faster than light. And the gap between those two statements is exactly where our investigation begins. Take your shadow. Stand in a dark room 10 meters from a wall and shine a laser pointer at your hand. Move your hand fast enough and the shadow it casts on the far wall sweeps across that wall. Now imagine the wall isn't 10 meters away, imagine it's 10 light years away, projected out into deep space like some cosmic film reel. If you rotate the light source even slightly, the shadow at that distance sweeps across a truly enormous span of wall in a fraction of a second. Do the math, and that shadow's edge is moving faster than light, much faster. Astrophysicists have actually used this exact principle to explain something we can observe directly. Rotating beams from pulsars, or the sweep of a searchlight's beam across clouds, can produce a spot of light that races across a distant surface at superluminal speed. Why doesn't this break Einstein's law? Because the shadow isn't a thing. It's not carrying energy from one point on the wall to the next. It's not sending information from point A to point B. Each point of that shadow is independently created by a separate photon striking the wall. The pattern only looks like a single object racing across, when in reality it's an illusion of continuity created by light arriving from a source, not a signal being transmitted along the wall itself. This is what physicists call a phase phenomenon, a mathematical pattern that outruns light without any actual carrier of energy doing so. The moment you try to use that racing shadow to send a message, say flash a code at one end and have someone read it faster than light at the other end, the illusion collapses. Information still can't outrun light, only the appearance of motion can. Now here's where the case gets stranger, because this shadow trick isn't a curiosity confined to laser pointers. It shows up on a genuinely cosmic scale, and astronomers have been photographing it since the 1970s. In 1971, researchers observing the quasar 3C279 using very long baseline interferometry, a technique that links radio telescopes across the globe to act as one enormous eye, noticed something that should have been impossible. Jets of plasma blasting outward from the quasar's supermassive black hole appeared to be moving across the sky at many times the speed of light. Some observations clocked apparent speeds at 4, 6, even 10 times light speed. Headlines at the time practically wrote themselves. Had astronomers just found proof that Einstein was wrong? They hadn't. What they'd found was a geometric illusion called superluminal motion, first explained mathematically by the British astrophysicist Martin Rees in 1966, years before the observations that would prove him right. Rees showed that if a jet of material is moving at extremely high speed, close to light speed, and pointed almost directly at Earth, the light it emits from farther along its path has less distance to travel to reach us than the light it emitted earlier from closer to the black hole. The result? The jet appears to close that distance gap faster than physically possible because we're watching two snapshots of light arrival times get compressed together, not watching the actual object move that fast. Rees essentially predicted a trick of perspective before anyone had the instruments to catch it in the act. When they finally did, in quasar after quasar, radio galaxy after radio galaxy, the apparent speeds violated nothing. The real velocity of the jet material, once you correct for the geometry, sits safely below light speed every time. The case resolves. Another one of Einstein's boundaries surviving direct empirical assault, once the illusion is stripped away. Let's move deeper into the file, because shadows and quasar jets are just the beginning. The next suspect is space itself, and this one is even harder to intuit because it involves something growing rather than something moving. In 1929, the astronomer Edwin Hubble, working from Mount Wilson Observatory in California, made an observation that would upend cosmology. Distant galaxies are receding from us, and the farther away they are, the faster they appear to recede. This became known as Hubble's law, and it was the first solid evidence that the universe itself is expanding. Here's the part that turns this into genuine faster-than-light territory. Because the amount of expanding space between us and a distant galaxy scales with distance, galaxies far enough away are receding from us at speeds that exceed the speed of light. Not a small excess, vastly exceeding it, for galaxies near the edge of the observable universe. This sounds like it should be the most obvious violation of relativity imaginable. It isn't, and the reason why is one of the most elegant resolutions in modern cosmology. Einstein's speed limit governs motion through space, the movement of objects relative to their local surroundings. It says nothing about the expansion of space itself. No galaxy is moving faster than light through its own patch of cosmos. Instead, the space between us and that galaxy is stretching, carrying the galaxy along with it, the way a raisin embedded in rising bread dough moves away from other raisins. Not because the raisin is crawling through the dough, but because the dough itself is expanding underneath it. Cosmologists sometimes describe this with the phrase metric expansion, and it's the reason the observable universe today is roughly 93 billion light-years across. Even though the universe itself is only about 13.8 billion years old, light hasn't traveled 93 billion light-years to reach us. The space it traveled through has been stretching the entire time. Here's the reveal that turns this into more than a footnote. Every single night, when you look up at a clear sky, you are looking at galaxies that, at this exact moment, no longer exist in a location we could ever reach, even with a ship traveling at light speed, because the space between us and them is expanding faster than light could ever cross it. There is a genuine boundary out there, physicists call it the cosmic event horizon, beyond which nothing, no signal, no future spacecraft, no message sent in any form will ever be able to reach us or be reached by us. Not because of a speed we haven't achieved yet, but because the space itself is outrunning the very fastest thing there is. It's not that we're too slow, it's that the finish line is retreating faster than any runner could ever close the distance. That single fact rewires how you think about the size of everything. The observable universe is not everything that exists. It's the portion of everything that hasn't already been carried permanently out of reach by cosmic expansion. There are galaxies, likely trillions of them, forever beyond any possible contact. Not hidden, not disguised, just receding into a silence that light itself cannot cross. We're now deep enough into the case file to bring in the piece nearly every viewer has heard of and almost no one understands correctly: quantum entanglement. In 1935, Einstein, along with physicists Boris Podolsky and Nathan Rosen, published a paper pointing out something deeply uncomfortable buried inside the new science of quantum mechanics. If two particles become entangled, linked in such a way that measuring one instantly determines the properties of the other, then measuring one particle here on Earth could seemingly determine instantaneously the state of its partner particle, even if that partner were on the other side of the galaxy. Einstein hated this implication so much he called it spooky action at a distance, and used it as an argument that quantum mechanics must be incomplete. For decades this stayed a philosophical argument until physicist John Stuart Bell developed a mathematical test in 1964, now called Bell's theorem, that could actually distinguish whether this spooky correlation was real or whether hidden ordinary explanations could account for it instead. In 1982, physicist Alain Aspect and his team in France ran the experiment. Entangled photons measured at separated detectors showed correlations that violated Bell's inequality exactly as quantum mechanics predicted, and no classical, hidden variable explanation could account for the results. Decades later, in 2015, teams in Delft, Vienna and Boulder closed the last remaining loopholes in these experiments, confirming it beyond reasonable doubt: entanglement is real and the correlation between particles genuinely does appear to establish itself instantaneously, regardless of distance. So did physics just hand us faster than light communication? This is where our case file demands precision, because this is the single most misunderstood result in modern science. When you measure an entangled particle, you get a completely random result. Heads or tails, up or down, there's no way to control which outcome you get. Your partner, holding the other entangled particle, also gets a random result. It's only when the two of you later compare notes, through an ordinary, light-speed limited communication channel, a phone call, an email, a radio signal, that you discover the outcomes were correlated in a way no classical process could explain. Neither person can use their own measurement to send a chosen message to the other. There's no dial to turn, no bit you can control, no information transmitted faster than light, only a correlation that can only be verified after both parties compare results using ordinary, speed-of-light limited means. Physicists call this the no communication theorem, and it's been proven rigorously. Entanglement cannot carry usable information faster than light, no matter how the experiment is designed. Einstein's spooky action turned out to be real, and yet somehow the universe still protects its speed limit. Correlation without communication. That's the resolution. Now for the piece of this case file that lives inside ordinary materials, not distant quasars or cosmic horizons. And it might be the strangest one yet, because it happens inside things you could hold in your hand. In 1999, physicist Lene Howe and her team at Harvard University slowed light down to 17 meters per second, walking pace, by passing it through an ultra-cold cloud of sodium atoms called a Bose-Einstein condensate. Later experiments by her team managed to stop light completely, store the information it carried inside the atoms themselves, and then release it again as a beam of light, essentially freezing a photon's information and playing it back on command. If light can be slowed to a crawl or frozen entirely, then logic says the opposite trick, speeding light's effective velocity beyond its normal vacuum speed, should also be possible in the right material. It is. In 2000, physicists Li Jun Wang, Alexander Kuzmich, and Arthur Dogario at the NEC Research Institute sent a laser pulse through a specially prepared chamber of cesium gas and measured the pulse emerging from the far end of the chamber, before the peak of the same pulse had even finished entering it. The effective speed of the pulse's peak was calculated at roughly 300 times the normal speed of light. Once again, headlines wondered if relativity had just been broken in a tabletop experiment. It hadn't, and the explanation involves something called group velocity versus signal velocity, a distinction almost nobody outside physics ever learns. A pulse of light isn't one single wave. It's built from many overlapping waves of slightly different frequencies, layered together. In specially engineered materials, the relationship between these frequencies can be manipulated so that the peak of the combined wave pattern appears to shift forward through the medium in a way that looks like it's arriving early. But no actual point of the wave, no piece of true information, no signal that could carry a message, ever exceeds light speed. The peak's apparent early arrival is a reshaping of a wave pattern that was already present at both ends, not a signal outrunning light between them. It's mathematically similar to our shadow on the wall. The pattern moves faster than light, but nothing carrying real information does. Wang and his colleagues were careful to state this themselves when publishing the results. The experiment demonstrated superluminal group velocity, not superluminal transmission of any usable signal. This is the moment in the case file where the pattern becomes undeniable, and it deserves its own reckoning, the reality check. Every single example we've walked through, the sweeping shadow, the quasar jet's illusion of motion, the expanding fabric of space itself, entangled particles correlating without communicating, light pulses reshaping themselves through cesium gas, shares one identical structure underneath. In every case, something that looks like motion, or something mathematically described using the language of speed, exceeds light's velocity. And in every single case, without exception, the thing that actually carries energy, cause, or information never does. Not once, in over a century of trying to catch nature breaking its own rule, has anyone found a genuine violation. What we've found instead is a universe with an extraordinarily precise definition of faster. One that permits patterns, illusions, correlations, and geometric tricks to exceed light speed freely, while guarding the one thing that actually matters absolutely, the transmission of real cause and effect. Light speed isn't a speed limit on motion, it's a speed limit on causality itself, the rate at which one event in the universe can influence another. Everything we've examined finds a clever way to dance right up to that line without ever crossing into genuine cause and effect at a forbidden speed. Why does this matter beyond satisfying curiosity? Because this single distinction, pattern versus signal, correlation versus communication, apparent motion versus causal transmission, is the load-bearing wall of nearly all of modern physics and modern technology. GPS satellites orbiting Earth have to correct for relativistic time dilation predicted by these same equations, or your phone's location would drift by kilometers within a single day. Particle accelerators like the LHC are built entirely around the assumption that mass can approach but never reach or exceed light speed. Quantum cryptography, real currently deployed encryption systems used by banks and governments, rely specifically on the fact that entanglement correlates without communicating, because that's precisely what makes eavesdropping detectable. Every satellite, every particle detector, every atomic clock, every deep space mission trajectory is calculated using a framework that has now been tested at cosmic and subatomic scales alike and has never once failed. There's a human cost buried in this story too, and it's worth sitting with. For over a century, brilliant scientists have wanted to find the crack in this wall. Einstein himself spent years trying to find flaws in quantum mechanics using exactly this kind of thought experiment, hoping to expose an inconsistency. Physicists chasing tachyons, hypothetical particles that would exist only above light speed, have searched for them in cosmic ray data and particle collider results for decades and found nothing. In 2011, a team at the OPERA experiment in Italy briefly reported neutrinos apparently arriving faster than light, sparking a worldwide scientific frenzy for months, only for the result to be traced back to a faulty fiber optic cable connection, a genuine equipment error, quietly corrected in 2012 once the team reran their measurements. Even in that embarrassing human moment of scientific error, the pattern held, the rule survived, and the mistake was ours, not nature's. That's what makes this rule different from most unbreakable claims you'll hear elsewhere. It isn't dogma. It's a limit that has been attacked, tested, poked, and hunted by some of the smartest people who ever lived, using tools that span galaxies down to subatomic particles. And it has survived every single attempt. That's not the profile of a law enforced by authority or assumption. That's the profile of a law describing something structurally true about the universe itself. So where does that leave us, standing at the edge of everything we've just walked through? The universe, it turns out, is not stingy about speed. It hands out superluminal motion generously, to shadows, to jets of plasma a billion light years away, to the fabric of space itself, to wave patterns bent through cold gas in a lab. What it refuses to hand out, under any circumstance anyone has ever devised, is a way to move real cause and real effect faster than roughly 299,792 kilometers per second. That boundary is not a wall we've failed to find a way around. It's closer to a definition, a kind of cosmic bookkeeping rule that keeps the universe's ledger of cause and consequence internally consistent, no matter how creative the illusion trying to sneak past it becomes. The next time someone tells you nothing can move faster than light, you'll know the fuller, stranger truth. Plenty of things do. Shadows do. Space itself does. The peaks of light pulses in exotic gases do. What can't, what has never, in a century of the most rigorous testing science has ever conducted, been caught doing so, is a signal, a cause, a piece of real information, slipping past the one line the universe seems determined to hold. If you want to keep tracing where evidence-based mysteries like this one lead next, subscribe and stay with the Reality Files, because the next case file is already waiting to be opened.